Welcome to my channel AI Basics with AK. Here we are with another new episode in Introduction to Statistics, the episode 5, the probability fundamentals. This episode is the most basic uh, fundamentals where we will try to introduce the concepts of probability which you would have learned in your middle school. So, what is a probability? The probability is how likely an event can happen. Say, for example, okay, how likely is it going to rain today or tomorrow? So, very likely or not impossible. So, it lies between an impossible event. Say, for example, in summer, when it is, say, every day it is approximately 38 degrees to 42 degrees Celsius, then it would be almost impossible or near impossible that it would rain tomorrow. Say, for example, if you are in Mumbai and it's a rainy season and it is in the month of, say, August, you would almost be certain that it is going to rain today or tomorrow. So the probability always lies between these two extreme values, which is impossible and a certain event. Ideally, it is very impossible for us to predict exact impossible and exact certain. So ideally, it is between those fractions, right? Now, say for example, I tossed a coin. So we do not know what has happened in the past. So either it can be a heads or a tails. Then we would say the probability of heads or tails would be 0.5, which is ideally we also call it as 50% chance. Make sense? Beautiful, right? Let's learn some of the important key terms in a probability. Ideally, how do you arrive at a probability? You cannot arrive it by intuition. In the earlier example, we have discussed about two examples. One is about the rain, predicting and rain, and second is an example of predicting whether it's a heads or a tails. In pure statistics terms, you should have an historical data to predict it. Say for example, in reality, you should be having all the data of all days, how much rainfall it has occurred in each individual day. So that becomes your sample space in the past. An event might be your full rainy days. Maybe, so for example, if it is raining greater than, say for example, 5 mm of rainfall. So I do not know the exact term. Maybe 5 mm is too large or too small. I do not know. I'm just giving a random number here. So let's call that as an event. In pure statistics terms, then you know that, okay, what is a probability that it is going to rain on any given random day in 365 days would be number of total days where how many days are there, that becomes your total sample space, that all possible outcomes, and the number of days where the rainfall is greater than 5 mm, that is your particular event. So how do you conduct a probability? You count all of them, all of these outcomes, and you divide it by the total number of outcomes. That becomes your probability of an event, whether it is going to rain on any given day at a random day, when you have collected when you have this information. That's how you arrive at it. Similarly, when you toss a coin, okay, if we extend this example, you have two possible outcomes and one can be your heads or a tails. That's how you can always arrive at this example. That is your number of favorable outcomes divided by the total number of outcomes. Ideally, in pure statistics, you cannot guess that there is only one possibility of a head or one possibility of a tail, because in pure statistics, like if you're a true data scientist, you should always question with data. You cannot believe, okay, the coin will always be unbiased. There might be a chance that the coin might be biased. Maybe 100% of the time it might be giving heads. So you go back, collect the data, you check the all samples, how many times it has been tossed in the past, that becomes your sample space, and then you collect the number of events, like number of tosses where it uh, it has been the result was heads. Say you have tossed for 100 times and heads has occurred, say for example 60 times, then your probability of heads will be your 60 divided by 100. Okay, so that's a pure statistical term of measuring a probability from historical data. Always in statistics or in data science, we arrive probability from the historical data, but not from the intuition in almost all the scenarios. Okay. Now, this is the most basic things. You understood that, okay, there is a sample space and you have an event space, and then the probability is nothing by number of events in an number of outcomes in an event divided by number of, so probability of an event is number of events, say number of events divided by the total sample space. Simple. I am not complicating it here. So always this number lies between your 0 and 1. This is a fundamental rule. And probability of sample, say for example, if we are discussing here as probability, it is always will be 1, because probability of a sample is nothing but number of sample events divided by number of sample events. Then of course when you cancel this results will be 1. Beautiful, right? And what is complement rule here? Means the number of times rain would not occur. So how do you say rain would not occur? When we go back to our Venn diagram here, if S is the total number of days and E is the days where rain is greater than 5 mm, S minus E would be the events or number of days where the rain is less than 5 mm. So if we extend the same thing here, P, where E complement here, I'm just following the same terminology, would be the sample events minus E divided by sample. So it will be 1. So I'm just doing that rule of number of E events by number of S. I don't know why I'm going to write it. So this becomes 1 minus E by S, which becomes your 1 minus probability of events. So your complement rule is nothing but your 1 minus P of E. So I could not write it in a very clear way, but since it's very simple, I hope you're able to understand it. Maybe in the next episode, I'll try to use a clear way of writing it here. Okay. Thank you. So this is the same thing. If the probability of rain is tomorrow, then probability of no rain is 1 minus 0.3, which is 0.7. The same thing that we have learned in our previous slide. Now, if there are two events that's not going to overlap, then how do you arrive at it? You just add those two events. It's as simple as that. Say for example, you rolled a dice once, and what is the probability that it is going to 1 or 2? In our sample space, we know that a dice has six sides, right? So the sample space is 6. So there are 6 possibilities. That's the reason our sample space is 6. And what are the events that we are trying to filter it out? It is either 1 or 2. So what are the number of events in our event space, which is 1 or 2? So if you want to predict the event that we are trying to predict the probability of event we are trying to do it, how many favorable outcomes are there? 2. And what is our sample space, which is 6? So which is nothing but 1 by 3. Similarly, if we can extend it to the same Venn diagram of 6 and the event for 1, it is 1 by 6. So the probability of, say for example, event of where the outcome of rolling a dice is 1 will be your 1 by 6. Similarly, the probability of an event space, if it is 2, will be also 1 by 6. When you add both of them, 1 by 6 and 1 by 6, the result will be also will be 1 by 3, because the result is 2 by 6, which is 1 by 3. So that's the reason when it is mutually exclusive event, it means one outcome is not dependent on another outcome, then we can add those two individual probabilities to arrive at a combined probability. Beautiful, right? This is a conditional probability, which is completely different from the mutually exclusive events that we have discussed here. Here we are trying. Let's bring back the earlier example of tossing a coin. In earlier, we have discussed something about biased or unbiased, if you remember it. Now we have an additional information where how the coin is phased when it is getting tossed, whether heads is pointing up roof or the tails is pointing roof. Now you have to predict a probability that given the heads is pointing the roof, what is the probability that it would be heads? In reality, you would see how a person is tossing it, right? If it is tail is pointing upwards or heads is pointing upwards. So accordingly, you can, this is the condition, right? The condition is that here heads is pointing upwards. We already know that event because we have already seen the person that heads is pointing upwards just before the toss. Then just while he is tossing, then we have to predict it whether it is a heads or a tail. That's the when that is when we can arrive at a conditional probability. Beautiful, right? You know that a certain event has occurred, then you have to correct. You know a certain event has occurred, which is event B. Here in the case, the person, we have seen that he has placed his coin with tails upwards or heads upwards, and you have to correct your probability based on this particular condition. That's when you say that it is a conditional probability event. Okay, let me not go through this formula at this point of time. Let me come with an example. In a pack of decks of 52 decks, you know that there are clubs, diamonds, hearts, and spades. Usually the clubs and spades are black in color, right? And hearts and diamonds are in red in color. Now, how many hearts will be there? Ideally, it is 13. And they are also red. And how many reds are there? Ideally, it is 13 and 13, which is 26. So, a probability of heart, which is and given red, is that probability heads and it is a red, which is nothing but your 13 by 52 because hearts is already red, and probability that it is a red, which is nothing but 26 by 52, which is 1 by 2. So what that is mean is that you have, so somebody is drawing a card and you have seen something as a red color, and you have to predict whether it is a heart or not. But since you know that it is red, your probability is 1 by 2, which is not 1 by 4, right? Because how many ideally earlier how many events are there? Club, spades, and heart and diamond. But since you have seen when he is drawing a card which is red, your sample space has reduced from 4 to 2, right? And number of out events reduced from has remained the same, which is 1. So in the earlier, if you do not know the information which is a red, the probability is 1 by 4. Since you have seen that information, the sample space reduced to 2, so it becomes 1 by 2. So that's the beauty of conditional probability. The extension of this is a Bayes theorem, which we will discuss at a later point of time. But the conditional probability itself is a beautiful, because you're shrinking the sample space because you have seen that some event has occurred just now. So you're reducing the sample space and you're improving your probability. You're trying to infer the probability based on this new learnings. The same thing we'll try to extend in Bayes theorem, but just carry this inference kind of a thing. I'm not going to explain this formula. The formula remains the same, but right now you have an AI or anything which directly, if you give an example, it gives you the answers. But the formula is probability of A intersection B, which is nothing but the number of events, which is both red and hearts at this point of time, divided by the total number of red events. That's you're trying to shrinking the sample space at this point of time. That's how it is. That's it from this episode. What we have discussed and how we are extending to the next episode is that we have seen the most important of this episode is learning of this episode is that the probability is between 0 and 1. Okay, and in the next episode we will try to extend these learnings into our statistics that we have seen in the earlier plots like box plot and everything, how we can see these distributions by plotting this in discrete and continuous events. Okay, so let's stop at this episode. I hope we'll continue this learning in the next episode. Thanks a lot for watching this episode. Bye.